Okay, it's time for our last talk in this afternoon. This talk will be given by Professor Hong-Jian from Shanghai Jiao Tong University. He's going to talk about massive gauge gravity scattering amplitudes, geometric and topological mass generations, and the double copy. Okay, welcome.
It's my great honor to be here for this talk. So first thing, I will certainly thank the organizers, especially Professor Yao, for creating this great and inspiring conference, and which brings many different physicists from different branches, different areas together to exchange and discuss. So it's my great honor today to give this talk, especially for this audience. I will talk something about our recent studies in connection to the massive gauge and gravity scattering amplitudes, and in connection to the mass generation, either geometrical or topological. So let me start with a brief review. And this slide, I'm trying to emphasize the conventional understanding of the so-called new physics normally refers to the discovery of the new particles. But in a more general sense, the new physics should refer to the discovery of the new, search for the new phenomenon, and eventually discovery of the new principles, and have a long list of the past important breakthroughs, starting from the spatial relativity, both the electric effect, general relativity, discovery of the particle spin, P and CP violation, and so on. All these breakthroughs concerning with new phenomena and eventually lead to the new principle. That brings the revolution for the physics. But yet, they do not concern any new particle. So starting from the last century, and the Marx-Molly experiment leads to the recognition that no acid. But it leads to the new revolution of the spatial relativity. Later on, the discrepancy in the precision of Mercury's helium. That's using the low in Newton gravity. The people already postulate the new planet, another new planet, a little planet. It's called Vulcan, but no discovery. Now we know shortly we know the real solution is the general relativity. So for the particle physics, almost 12 years ago, the discovery of the LHC seems to complete the standard model. So it's important to ask what's the implication so far for the long discovery of the LHC. So some people are very excited, believing that the new physics is white and color, and some people are very pessimistic. So I am probably in the middle. So this slide is a summary on the structure of the standard model. I call it 1, 2, 3 theory. And certainly there are two big missing issues. That's the dark matter and the dark energy. And these two, the existence of these two has been well established for many decades, based on the gravitational interaction at large distance. But not yet there's no any other direct evidence. So the major issue is that in the standard model, we do not have the successful incorporation of the gravity into the standard model Lagrange. So what happens is no full understanding of the quantum gravity at both largest and smallest scales. And there are many intriguing, important features in connection to the quantum gravity. For example, the IR-UV correspondence. That is, at least I personally believe, that has something to do with the dark energy in connection to our recent study like the holographic dark energy. I will not have time to discuss those. Instead, today I will highlight some of the importance of the equality and the square law. It looks like that's the preference favored by nature. Starting with in mathematics, we have this Pythagoras theorem, and that extension leads to the Fermat's last theorem. However, it takes more than 200 years to finally establish the n cannot be larger than 2. So there's only integer solution for n equals 2. That's emphasized the uniqueness of the square relation. In the spatial relativity, the mass energy equivalence, if we write in the Lorentz invariant way, that is again the square relation. That's the p mu square or momentum square equals to m square c square. And in the general relativity, the inertial and the gravitational mass equivalence, that is equality. And in the past 20 years or so, it has been a major direction for starting another fundamental relation between the gauge force and the gravity force. That is the so-called gravity equals gauge series square. And that has been established for quite a while for the massless case. And my talk today will be focused on what happens to the massless case. So I would first emphasize, highlight what is the challenges for the mass generation. So we classify all the particles according to their spin. So starting with the spin 0, that's the Higgs particle, the Higgs boson. So either massless, it's a scalar, spin 0 scalar, or massive. Right? So the physical degree of freedom, that's the same. That's 1 equals 1. That is, brings the one of the biggest partial in the particle physics in the standard model. That's the so-called hierarchy problem, because after quantum corrections, that there's no way to protect the Higgs mass, the large quantum corrections. On the other side, for the quarks and the leptons, which are Dirac fermion, contains the left-hand fermion and the right-hand fermion. For example, left-hand electron or right-hand electron. That's the two wild fermion. Combine them, they can form the Dirac mass term. So that's 1 plus 1 equals 2. So in the massless and the massive case, so the physical degree freedom equal again. If there is no electroweak, there is only QCD or electromagnetism, then there's no way to protect the quark and the lepton mass. You can get arbitrarily large mass for them. However, the standard model is smart because in the standard model we have the electroweak SU2 cross U1 theory. In which we have the polarity violation. So that means the left-hand the fermion and the right-hand fermion are not in the same representation of the SU2. So that is the requirement, almost unique, to impose the fermion can only obtain a mass through the Higgs boson, through the Euclidean interaction. So that in a way to define why the fermion mass has to be stay at the weak scale. That in the massless case, I mean, in the massive case, for example, electron, we have the left-hand electron and right-hand electron, I call it psi L and psi R. That are two wild fermion, okay? In the massless limit, you just end up with the left-hand the electron, the right-hand electron decoupled. They are two massless wild fermion. No, it's just the mass term. This mass term has a smooth massless limit. When you take this limit, the physical degree freedom does not change. The same thing happens for the Higgs boson. So that's the one of the biggest motivation, the partial in the standard model, so-called hierarchy problem. So there's no way to protect the Higgs boson mass after quantum corrections that Higgs mass will be brought up to even Planck scale. So that some additional motivation for supersymmetry, whatever, to resolve this so-called hierarchy problem. So the fermion so far sounds okay as long as we accept the fact that in the standard model, the polarity is violated. And the left-hand fermion and the right-hand fermion are not in the same representation of the weak interaction. The more non-trivial thing is concerning with the spin 1, the spin 2 particles, the gauge boson, and graviton. Explain more on what? Spin. Oh, what is spin? Oh, sorry, you don't know what is spin. So spin is I think this need to be really emphasized. Spin is one of the most important concepts starting from quantum, starting from spatial relativity. So I mentioned, sorry, my first slide, I mentioned, in the past 100 years, starting with spatial relativity, photoelectric, the GR, and the discovery of the particle spin. So that is in 1920 or so. It was discovered that the electron has a non-trivial quantum number, the quantum degree freedom, that's its spin. The classical concept is similar to like the Earth has an angular momentum. It is a type of the angular momentum, but it's intrinsical. So actually that was built in spatial relativities in the Lorentz group. So in that sense, I would claim the spatial relativity is labeled a classical theory. I think it's the wrong concept to say that the spatial relativity was a classic theory, but the spatial relativity is the LC. Oh, sorry, again. Yeah, so here that's one of the big issue. Probably you are not in particle physics community. You probably are in math or else. So sorry, I have to. For particle physics, that LC is a so-called large hadron collider. Is a proton-proton collision. One of the current is the most powerful current experiment located at CERN at Geneva. So almost 12 years ago, 2012, it's also exactly 12 years ago, 2012, July, there was a discovery of the Higgs boson with a 125 GeV particle. And the discovery of that particle is extremely important, as I mentioned here. This is the standard model Lagrangian, the whole standard model Lagrangian. In which formula? Right, that's too long, yeah. So maybe I can explain to you afterwards. Okay, sorry. So, yeah, so now I want to emphasize for the gauge field, a massless and a massive, they differ by physical degree freedom. So the massless gauge boson, like photon or gluon, only has is a spin 1 with the 2 helicity plus minus 1. And the massive gauge boson, for example, the W boson, it will have the 3 polarization, 3 helicity states, that's 0 plus minus 1. Okay. For the graviton, it's also interesting. A massless graviton in GR only has 2 helicity states, plus minus 2. So that's all these are determined by the Lorentz group. And it's a massive graviton, then there will be 5 degree freedom. So there are additional, like photon, like the gauge boson case, there's helicity 0 states. For the massive graviton, there are also additional helicity that's projecting the spin 2. That's the plus minus 1 and 0. So that's 3 more helicity states. So they do not equal. So that's the rises after the non-trivial issue for the mass generation. So the Higgs mechanism can be more general than Higgs boson, as I mentioned in the standard model Lagrangian. The Higgs boson is the scalar particle that provides the masses to all the standard model massive particles, including gauge boson and fermion. So, in a more broad sense, the Higgs mechanism refers to the spontaneous breaking of the continuous local gauge symmetry, while having original interacting Lagrangian respected this symmetry. So that's the general feature. It converts the would-be Goldstone boson into extra component of the corresponding gauge particles associated with the broken gauge generators. That generates the mass for the gauge particles. And also at the same time, it consistently conserves the physical degree freedom. So in the general sense, we can classify, now we know the Higgs mechanism can be conventional, like in the standard model, or geometrical, or topological. So the conventional Higgs mechanism is spontaneous empty breaking, electroweak empty breaking, by the vacuum excitation value of the Higgs boson. The geometrical Higgs mechanism is a spontaneous symmetry breaking of either the gauge symmetry of higher dimension, for example, or the dimorphism of the GR by extra dimension, in extra dimension compactified. The topological Higgs mechanism, I put a quotation mark here because there is no additional thing like the Higgs boson. There is no spontaneous empty breaking at all. You have the gauge invariant mass term, except that mass term is compact. And the important point I want to mention is that there is a dynamical conversion of the critical degree freedom associated with that topological mass term. So this slide gives you more detail, like in the standard model, as I mentioned, the gauge boson obtain the mass through the weak gauge coupling times the vacuum value of the Higgs boson. The Fermi obtain the mass through the Higgs vacuum excitation value times the Yukawa coupling. In extra dimensional compactification, it's totally different. It's a geometrical mass, like if you take the flat extra dimension and those masses of Kaluza-Klein states will be like determined by the radius of the extra dimension, 1/r. So that geometrical mass is, as long as you have extra dimension, it's for all the particles living inside, including like the geometrical masses for the gluon excitation, or the fermion excitation, or graviton excitation, we call the KK graviton and so on. So the topological mass term for the gauge boson on the graviton, the one of the intrinsic thing important for condensed matter physics is that the 3D, the Chern-Simons theory. You have the Chern-Simons term, that Chern-Simons mass term is gauge invariant, and it causes the dynamical conversion of the physical degree freedom, and their work gave us highly non-trivial prediction, as I will mention later. So the geometrical Higgs mechanism, we have a long series of papers along this direction, but let me starting with the simplest concept. So the Kaluza-Klein compactification of the extra dimension is to a massive KK states, including the KK gauge boson, the KK graviton. That's the most important thing. And those KK states obtain the geometrical masses by compactification. If you want to compactify any extra dimension, I will show you shortly. It's an intrinsic consequence to get those KK excited states, which are massive with a geometrical mass. And that compactification is through the spontaneous gauge symmetry breaking, right? Or that is why we put the quotation mark here, still called a geometrical Higgs mechanism. This actually was formulated for the massive KK gauge boson at the Lagrangian and S matrix level almost by me and my collaborators more than 20 years ago. And actually, even in 1980, mid of 1980, Michael Duff and collaborators, they found out that the massive KK graviton at the Lagrangian level is through certain geometrical mass generation. So recently, we have formulated the KK graviton, the mass generation for KK graviton at S matrix level, the scatter temperature level. We have a series of papers along this direction, including one new study in last month is evolved the geometry. So that concept, the simplest concept of the extra dimension was proposed about 100 years ago, 1920s by Kaluza-Klein, and they realized if there is a fifth dimension, and that is compactified on a circle S1, and then you all have the consistency with observation. And it is very simple, and let's start and consider a Yang-Mills gauge series SU3, the QCD or SUN, on an extra dimension, the 5D. If you add another simple parity like Z2 or before, that S1 reduces to an interval from 0 to L. And that gauge field have the normal A mu and additional fifth component A phi. And with proper boundary condition, and you make big expansion and so on. And certainly there will be a very general consequence, that is the 5D masses theory, the P's will vanish, 0. But it's the 4D momentum square minus P5 square. The P5 is quantized due to the boundary condition. So that is why we have effectiveness in a compactified space-time, 1 plus 3 dimension. We will see a Kaluza-Klein tau with R n over R. That n is an integer, starting with the zeros, that's the standard model particles, and go 0, and all the other infinity tau of take excitation. So that mass generation is geometrical, and will give us important consequence. And you could consider different geometry. I mean, the one of the most nowadays popular for the phenomenological study is the Randall-Sandel model, the warped 5D with this warp factor, and you have either physical coordinate, conformal coordinate, and do that more compactification. So for the gauge field, we make this boundary condition and take the expansion, and you can actually fix the gauge. So the, for example, 5-dimensional QCD, you add up a gauge fixing term because it's gauge involved in 5D. So in 4D, then you will find those KK excitation states. The massive KK states has a longitudinal component and 0 scattering amplitude, and their corresponding the fixed component become to be a kind of the ghost model. Actually, it's absorbed into the longitudinal component A5. There is a dynamical conversion, this so-called geometrical Higgs mechanism underlying this compactification. And that actually is formulated by the equivalence theorem at the S matrix level. So actually, the consequence is that you can calculate the longitudinal scattering of those KK gauge field, for example, KK Grua. And there are internal exchange of those 0 modes and KK states, but there's no Higgs boson involved. And in addition, if you calculate the scalar, the corresponding ghost boson scalar A5 amplitude, and there's no contact term, there's only exchange of the 0 modes and KK modes. And the energy dependency is obvious because this external scalar states has no energy dependence. And each vertex has the 2 scalar 1 gauge boson. So that's the 1 momentum e to the first power. So divided by the denominator, the propagator. So that this whole diagram behaves like the e to 0 order, the constant, so has a good harmonic behavior. But on the other side, and for those diagrams, it has a longitudinal polarization for each external states. Each external polarization is proportional to the first power of the E. So you by simple power counting, that's the e to the 4th power. The similar thing for this type of a diagram. And then you will find all the e to the 4th power. Here I characterize by e over m, so that's x to the 4th power cancel out. And then you end up with those e squared terms left here. But again, due to the Jacobi identity, all those e squared terms geometrically canceled out. So this is totally different from the standard model 0 modes with the Higgs boson exchange. So now in a more general formula, you calculate, for example, the 4-point gauge boson scattering and the KK gauge boson longitudinal, and it corresponds ghost boson A5 scattering amplitude. And these 3 group factors satisfy the color Jacobi identity. And if you require the e to the 4th power and the e squared term cancellation in general, and those that will impose the sum rule condition for the cortical and the cubic gauge coupling. And that is a condition given here. And this general condition can be verified for each given extra-dimensional model, for example, a flat 5D model or a Mandel-Sandra model, can verify this explicitly. And finally, at the e to the 0th order, these two amplitudes we want to establish their equivalence. And that equivalence give you a condition. I mean, that equivalence, if we have those purple conditions for this coupling, all right, so this cubic coupling, I mean, this additional Jacobi identity, color Jacobi ensure this is vanishing. So lately we found that there are even simpler things. Just calculate the 3-point amplitude. That's the 2 longitudinal gauge function, 1 transverse gauge function. So that's 3 points. You can do the calculation with the 2 A5 AL replaced by the Goldstone version A5, and this transverse state remain the same. And you found that in fact this diagram will have the energy dependence e to the 4th power superficially. But in the end, you end up with the e to the 1st power. It's the same as this Goldstone amplitude. So there's actually, so 2 longitudinal external states, so E square with the coupling of the E, so that's the E cubic. And on this side, it has to be cancelled down to the E to the 1st power. And also the lowest order of the E to residual E to the 1st power term have to be equal on both sides, and this is reflected by this coupling mass condition, a fundamental condition given here. And this, again, this condition can be proved explicitly for each given model. And finally, we found that the endpoint KK amplitudes, right, and the corresponding equivalence between them can all be reduced to this most fundamental 3-point amplitude and condition. So that actually is the simplest amplitude I have ever computed for new physics. Okay, so extremely simple. So the graph here lay out our strategy. So now we're starting with the 3-point KK gauge model amplitude and their equivalence theorem. You can reconstruct the 4-point, as I mentioned earlier, and those identities, I mean, I gave you here for the 4-point, can all be reduced back to the 3-point. And then through the double Kobe, I will mention later, and you can, through the 3-point gauge model amplitude, you can construct the 3-point graviton amplitude, massive graviton amplitude. Then from the 3-point graviton amplitude, you can construct the 4-point or even higher point graviton amplitude. And those 4-point or higher point graviton amplitude is, in high energy limit, is connected to the 4-point or higher point gauge model amplitude through the double Kobe. I mean, this picture generally for any experimental model, but for the warped case, this is confined in this high energy limit. This can be explicitly established. So next topic is I space to further discuss the geometrical case mechanism for the bigger graviton mass energy. Now I finished the gauge model have for like the bigger gluon and so on. Any questions? So if not, I would just mention now you can put the Einstein-Hilbert action in 5D. And now we are doing perturbative calculation, expanding through the Minkowski matrix. And the Lagrangian term contains the 0th order, the first order, the first order, the second order in kappa. And that 5-dimensional graviton field contains, you can write down by the 4-component part. And this H55 is a scalar component that will, after compactified, will become to be the Hessian 0 state of the longitudinal mass of graviton. And this H mu 5 originally in the Kaluza-Klein theory, it was attempted to identify a photon for its 0 limit. So now in general, now this H mu 5 actually will be absorbed those KK states. If you properly choose your boundary condition, you can remove its zero modes, and those KKs, as vector KK states, will be absorbed by the massive graviton field with the helicity plus minus 1. So here is a more clear definition given here, and if you add imposing the simplest compactification with S1 plus Z2 orbital, and we can make a KK expansion and derive the quadratical KK Lagrangian contains the bilinear term. You see there are mixing term between the graviton and this V mu, H mu 5, or H mu nu, and different type of the mixing, and the H and the phi, which denotes the H5 phi. What? Oh, M is a mass. Is the KK mass for graviton. Okay. So then we need to fix the gauge because we are starting with a gauge invariant theory, only compactify on the boundary. So that gauge friction term is a generalization of the zero modes massless GR gauge friction. So that's will contain additional thing inside, which those, especially those ghost tone fields, which are important. So then we gave this non-trivial graviton, massive graviton propagator. And it contains this physical pole and some additional unphysical pole shown here. So the interesting thing is that we can take a Feynman gauge. So that propagator has been greatly simplified. That simplify, you see the numerator, right? So it's very simple. It's like the GR, massless graviton, except in the denominator we have a mass term. On the other side, when we take this precise gauge friction parameter go to infinity, we go to the unitary gauge, and we recover the numerator. This is the massive graviton propagator, right? More familiar for the people playing with this massive gravity before. So we have the minus 2/3, that famous coefficient. So then the non-trivial thing is for our case, the KK graviton propagator, you can take the massless limit. That's the smooth limit. You end up with like a Feynman gauge, this propagator. This is precisely a massless graviton propagator in GR. Okay, with this coefficient of 1 minus 1. Okay. Eta is the Minkowski matrix. The delta means the KK index of the propagator has to be the same. The N and the M has to be the same. So the conventional massless graviton propagator, I mean, this is conventional graviton masses in GR. You can take the Feynman gauge. So that's the conventional graviton propagator in Feynman gauge. We compare these two. They are exactly the same, except this trivial factor delta and M for the KK index. So that means the KK theory has a consistent mass generation, and it has the smooth masses limit without the so-called weighted discontinuity. I mean, conventionally in 1930s, there was the famous work by Fields-Pauli. They added it for the first time under the Lorentz invariant mass term for the graviton in GR. And then if you derive the propagator, you will have this very strange numerical factor coefficient 2/3 getting here in comparison with this massless case. So if you take the massless limit of this propagator, that will later reproduce the numerator. So that's called the random Welterman-Zaharo with discontinuity. So that discontinuity actually now we know is an indication of the inconsistency of all this type of the Fields-Pauli type gravity, massless gravity. It has been well well popular, widely applied in gravity field for the people studying gravity. So, but however, this is inconsistent. The reason for that discontinuity is because the massive graviton has a 5-degree freedom and the mass is 2. The 5 does not equal 2. However, for the KK case, that geometrical Higgs mechanism ensures, I mean, we're starting with the massive graviton and we go back to the massless limit. That means you take the extra dimension to be extremely small, decouple all those KK states. Though then that massless limits will recover, I mean, the Goldstone boson absorbed, I mean, this H mu 5, H55 absorbed by H mu now is released to be the massless physical component. So that's the 2 for the original 2 for helicity plus minus 2, and the H mu 5 is given here plus minus 1, and the H55 is the scalar given here. So that's 2 plus 2 plus 1 equals 5. So that also singles out the Kaluza-Klein compactification as the truly consistent theory for massive gravity. And that geometrical Higgs mechanism can be, I mean, through the compactification can be formulated through, now we call it the gravitational equivalence theory with type 1 and type 2. The type 1 is basically tells you the helicity 0, now shooting the graviton state, the amplitude in the high energy limit will equals to that H55, the scalar component, which was eaten by, through the computation by the H mu. The type 2 is saying that we can calculate the physical graviton amplitude with helicity plus minus 1, helicity 1 amplitude. And that in the high energy limit will equal to the corresponding H mu 5 amplitude. Here I use this rotating wave to denote H mu 5. So that's the vector Goldstone boson amplitude. These two are equal. So that also brings up the important consequence. That means the high energy behavior of this such KK theory is much, much better than the conventional field Pauli type of massive gravity or any other massive gravity. For example, if you do power counting and the n-longitudinal graviton amplitude with helicity 0, I will have the energy dependence power that's n plus L plus 1 times factor 2. The L is the number of the loop. And then corresponding, because of the equivalence theorem, these two amplitudes has to be equal, of course, including the energy dependence. So the endpoint phi, the H55, the Goldstone amplitude, there is no external polarization. So that energy dependence is simply L plus 1 times 2. And that difference means the energy cancellation involved in the longitudinal amplitude endpoint. The longitudinal amplitude has to be by a power, energy power of the 2n. Then for the helicity 1, again, that the cancellation is less severe because it only involves the vector Goldstone boson. Here it's a helicity plus minus 1, and its external state has a polarization energy dependence of 1. So that is cancelled by a power of the e to the nth power. And finally, we can also calculate the KK gauge boson amplitude. The power counting gives you that's the e to the fourth power for the endpoint. And the corresponding Goldstone boson A5 amplitude gives you something like this: 4 minus n minus another number, depends on the number of external lines, odd or even. So that energy cancellation down is basically by power of the n. And in the odd case, will be plus 1. So in here, I show you more clearly. I mean, if you consider the 4-point graviton amplitude, longitudinal graviton amplitude, like this. I mean, the naive power counting of each individual diagram will have the energy dependence of e to the 10th power. And finally, that's the highly non-trivial cancellation, a series of cancellation down to the e square term, determined by the corresponding Goldstone amplitude. So by 8 power by a power of the 8 in energy. And later I will mention that actually is connected to the double copy of the gauge boson, because gauge boson is cancelled down by 4 for the 4 point. So 4 times 2 is 8. So basically that is determined, back to this picture, is determined, the graviton amplitude is determined by that and its cancellation involved, so the double copy is determined by the corresponding gauge boson and its cancellation. And I'm glad these two are connected because of this double copy relation. So that's explicit calculation for the 4-point amplitude, and in the general compactification setup, and you have a general coupling. And for this to hold, and that condition, this is a highly non-trivial condition, has to be satisfied. And actually, we prove if we further compute the 3 points, and that condition can be further reduced down to the 3-point condition. This is the simplest graviton amplitude. I mean, earlier days, the people calculate the 4-point or higher points. You will never be able to show up analytically in 1 page, and we have just a few lines. We can give this 3-point amplitude. This is the leading order, and the full 3-point amplitude is probably less than half page. And that cancellation involved here is e to the, with a 2 longitudinal graviton and 1 transverse graviton. There is e to the 6 cancellation to the square. And the 3-point, then further you examine, after cancellation, that leading order non-zero amplitude of the 2 longitudinal graviton and the 2 ghost boson phi are equal. And that equality is ensured by this condition. And this 3-point condition, you can verify this for each given model, either flat model or standard model, whatever. That can be proved, explicitly proven. Once we have that, starting with this 3-point condition, we can deduce the n-point amplitude in high energy limit, and the corresponding equivalence can be proved through this condition. And in here, the graviton case, we have the cancellation of the e to the 6th power to e squared. And for the type 2, that means the graviton has a helicity plus minus 1. The corresponding vector goes on both ways getting here. Again, we can verify this equivalence at 3 points. And the corresponding condition is getting here. And that involves the cancellation to the 4th to e squared. That can be now well understood. So this is the schematical summary on the whole business we are playing here. Now we can start with the 3-point gauge boson, take a gauge boson amplitude, which I'm making here, or the ghost boson amplitude. So that reducing or constructing, you can construct the 4-point. The 4-point amplitude will be, that equality will be reduced to 3 points. Because this is the most basic relation. And then, so the double copy for the 3-point and 4-point, you can get the corresponding 3-point graviton amplitude and 4-point graviton amplitude, or even higher points. So now I move to my last talk on the double copy. So that might tell you, starting with the QCD amplitude, the Zulu amplitude, to get the graviton amplitude. And this has been a major evaluation for amplitude area. That was established for quite some time ago, at least the BCG, the QFT setup was 2008, and the KLT formulation was establishment analyzing the closed and open string amplitude, and with this relation in the low energy limit. And that was proposed in 1980s. So almost take 20 years, the people realized that such a double copy relation can be realized in QFT. But so far, I mean, they are all discussed in the masses case. So we are asking, I think, an important question is what happens to the massive Kaluza-Klein theory? Or later on, we ask for the Chern-Simons theory. In fact, through the string setup, we know there are at least 6 extra dimensions. And that compactification will need to a lot of those massive KK states. The conventional KLT setup is you calculate for example, the open string amplitude. You get the closed string amplitude expressed in terms of the product with the open string amplitude. This is 4 point or even 5 point. Now you take the field theory limit, you get this graviton, massless graviton amplitude, the 4 point or 5 point. In terms of the corresponding the gluon, the color ordered gluon amplitude. And it takes more than 20 years. The people, the group in UCLA, they realized through this color kinematic duality. So you impose this well-known color Jacobi identity and another non-trivial Jacobi identity for the numerator. And that you can starting with the massless gluon amplitude in STU channel. And you just by replacing the C, each C to the corresponding numerator n, you get this graviton amplitude in an exact sense. So now we are asking what happens to the massive case. It turns out to be highly non-trivial because you can do a different type of the compactification. For example, we choose the simplest one with R before C2, then it doesn't work. So then we end up with try to resolve that and try to use the first principle approach, starting on string KK amplitude. And it turns out even though string theory has been developed since the last 1980s, but there are very, very few calculations on the KK, and most are starting the 0 mode amplitude. So if you start in the KK amplitude seriously, if you found this is open string amplitude with the KK number, each of the KK number of the external, that's the 4 point, and you need to sum up the different configuration of the KLT relation is, I already mentioned here, that's by 3 physicists around 1985. So what they proposed is you can calculate graviton in GR, the graviton amplitude, as a product of the two, the closest string amplitude, actually. In field theory, that's graviton amplitude, as a product of the two blue amplitude. That's corresponding to the open string amplitude. That's actually one slide earlier. That's shown here. And now you take the field theory and you take those. But then it takes another 20 years, 23 years. The people realized how to totally formulate the whole thing within the QFT. Now you can write down a more elegantly this color twist blue amplitude. And then you make a square on that, right? So that's simpler than this color ordered thing. It's more instructive, more instructive anyway. So if you do this whole massive KK things in a consistent way, we can get those non-trivial relation between the massive closed string amplitude and the massive open string amplitude. And now we take the field theory limit. That's what we obtain shown here. So especially that there are different channels of the combination contribution, and some of those terms, certainly depends on how you compactify. You have to make sure, you do have the string theory realization. If you don't, for example, if you have the R before the construction, that will be more complicated. You will redivide those. So here is a discussion on a more general treatment of the massive amplitude H boson to graviton. So recall that for the massless case, following up this BCG formulation, this is the STU3 channel. for the gluon amplitude. And if you double copy, you get this square, right? So the NS square, NT square, and U square for the graviton amplitude. And certainly, this formula has a nice symmetry. That's the generalized environment under the generalized gauge transformation. And certainly, you want to ensure that the physical graviton amplitude you construct it to be also gauge environment. And it turns out that delta M, the graviton amplitude, the delta A given here is basically the color Jacobi identity ensure this is gauge environment. So for generalized gauge transformation. The graviton amplitude now will contain this two term, and this is pure kinematics, S plus T plus U vanish. And the first is the kinetical Jacobi identity. That is a crucial component for the BCG construction, and SMT U to BCL. So now we want to extend this to a massive case. So if you do double copy for the massive graviton, take a graviton, you have a structure like this. But in addition, we certainly have a generalized gauge transformation for the take a gauge boson, take a gluon amplitude. And then we need to require this massive graviton amplitude to be environment under this generalized gauge transformation for take a gluon. And that condition leads to this. And then this one, the sum of the SJ, right, is for 4 point is the 4 external mass square. So this is the mass, so-called mass spectral condition. It turns out this is highly non-trivial. It's not always satisfied for any massive theory. This is the summation of this KK. Oh, sorry. This is the kinematic index. S1 is S, S2 is T, S3 is U. Okay. So this condition turns out to be highly non-trivial. Not all of the massive theories would satisfy. For example, the field Pauli type of the theory, the people tried very hard with this so-called DRGT construction. They make this work for the 4 point, but then for the 5 point, it fails. Because that is they're starting with the inconsistent massive gravity theory. So now we want to ask, starting with this 4 point spectral condition, how to solve it and what's a solution. But certainly we can take the flat 5D toroidal compactification on S1. Then we can straightforward to verify this condition, right? So you substitute because each mass is proportional to take an index. So you end up with this N1, N2, N3, N4 sum to be vanishing. This is nothing but just the KK number combination. That's the basic momentum combination. That can be ensured if you do a toroidal compactification on S1 with the periodic boundary condition. But however, if you have the orbifold compactification or with this warped 5D RS construction, that do not naively apply. So actually, we can generally solve this condition, and starting with the 3 very modest condition assumptions. Number 1 is a massive theory contains at least 2 types of the particles with unequal mass. That's something would be quite generic for a non-trivial theory. There exists only one simple pole for each STU channel. Number 3 is each scattering amplitude should include the contribution from all 3 kinematic channels of STU. So what then we can prove is the toroidal compactification of the flat X dimension is the unique solution. And we have the long paper over 70 pages with there's one section discussed about this proof. The main idea is to identify the group structure underlying this condition, the spectral condition 1, as a product of the integer group, the R, with the rank R, in a finitely generated abelian group. So then we proved that the unique solution to that within this group structure would be for the mass, arbitrary mass with the index k has to be proportional to the k square times the m1 square for the case of the R equal 1, the rank 1, for the rank larger than 1, we have this general condition. This all precisely matches to extra dimensional compactification with R equal to delta or R equal 1. So, and also as a byproduct, you can straightforward to deduce that also that index K has to be conserved. So let me take my still have probably another 5 minutes for the topological mass generation and the scan amplitude. This is also something interesting to us because the Chern-Simons theory has been widely used, especially for condensed matrix because you know what I mean. So this is the Chern-Simons gauge theory, the non-ability, non-trivial case. This is QED, this is the QCD, the Amels case. And that mass term is gauge invariant if this geometry correlation is satisfied. That means the mass term M is related to the Chern-Simons level. And for the topological mass of gravity in 3D, and this is the corresponding gravitational Chern-Simons term, like in this form. And the interesting thing is if you check on the equation of motion for the Chern-Simons gauge boson, right, so you find that the unshield gauge boson has in 3D has a 1 critical degree freedom. And that polarization vector you can write in this form. And there are additional 2 uncritical polarization. That's what we call the transverse polarization and the longitudinal polarization, the epsilon L and epsilon T. And there actually is a non-trivial relation is the epsilon T plus epsilon L gives you the physical polarization. That means the physical gauge boson in 3D massive case is composed of the transverse and the longitudinal, the sum of them. So then we know in the masses limit, the 3D, we have just this transverse physical 1 degree freedom for the transverse gauge boson. We would expect that now we are allowing, because we have the gauge invariant mass term, to take the masses limit. So this too will have the correspondence. So in here you would say, I mean, this too, if we take the high energy limit, we would expect this physical gauge boson amplitude again will involve this dynamical conversion equal its transverse amplitude in the high energy limit. This law we formulate for the first time called the so-called topological equivalence theorem. That the topological mass term, the Chern-Simons mass term, involve a dynamical conversion of this two. So that also have a highly non-trivial consequence. For example, this can be straightforward to establish based on just the 3D gauge invariance. And if you count the physical gauge boson amplitude, right? So that leading energy dependence and the corresponding transverse gauge boson amplitude, then there will be a energy power dependence reduction by power of the e to the nth power. And for the physical graviton amplitude, there will be an energy cancellation of the 3n plus L. A trilogy, that's basically is 4 point is 3 plus 4 times 4 is 12. So for the gauge boson, we can verify this topological equivalence theorem, and also the energy cancellation from e to the fourth to e to the zeroth order for n equal 4. And actually, this table is an explicit demonstration how this S is the Manstein variable. Basically, it's a scale like E squared. So this e to the fourth cancellation, e cubic cancellation, and e squared cancellation, and e to the first power cancellation, square root of the S, that's e to the first, all cancel out. So then we have to still further establish this equivalence that e to the zeroth order. This indeed work, as we, I don't have an explicit formula given here, but it's given in our paper in detail. So there is a, for that Chern-Simons massive gauge amplitude, the 4 point has the e to the fourth power cancel down to the constant into the lowest order. And then the non-trivial thing is we further calculate for the massive gravity. That graviton amplitude, the physical graviton amplitude will be the 3 times the external line, length of the external line. If it's 4 points, so that will scale like e to the 12th power. So that's now we can make a double coping using the Chern-Simons gluon, the Chern-Simons QCD with the gluon, massive gluon amplitude, without any Heinrich expansion. And now you make a double coping to here, and then you make it for the 4 graviton, physical graviton, Topological massive graviton amplitude, and you make a Heinrich expansion. It turns out the leading term is not the E square, right? Is the square root of the S is the E to the first power. So then we have the highly non-trivial, totally different from the KK theory. So KK theory, the 4 points starting with the E to the 10th power. Here is the E to the 12th, down to E to the first power, while in the KK theory, we always have the E square term at the lowest order term. So that involves the 11th order of power in energy cancellation. And actually, the double copy tells us straightforward there will be a cancellation of the E to the 12 down to the E to the 4th, because 12 minus 4 equals 8. 8 equals 4 times 2. So that's determined by the gauge, the gauge motion cancellation I just shown here. So that non-trivial thing is the E to the 4th power further cancel down to the E to the 1st power, as given here. It's showing here. This can be explicitly verified order by order. That has something to do with the particularity of the 3D gravity theory, because the mass is limited of the 3D graviton has no physical degree of freedom. So that cancellation I'm showing here, the double copy or the CK duality ensures the E to the 12 down to the E to the 8th, and further the gauge transformation down E to the 4th. And then finally, we have the E to the 4th down to the first power of the E. That amplitude is given here, the leading order non-zero amplitude. So that's the summary shown here. It's quite significantly different from what we found for the massive graviton, the KK graviton in 4D, compactified case. So finally, let me summarize again this one slide. So this is the fundamental relation, and I think it's important relation that connects to the standard model gauge sector, to the unknown, the graviton sector, to most of us. That graviton sector actually now we believe is the major reason behind the dark energy and the dark matter. So that one we have in this talk majorly discussed what happens to the massive case, and the mass can be explored along this direction. Okay. Thank you.
Okay.
There is another mechanism of mass generation without involving any symmetry breaking within an anomaly-free symmetry group called the symmetrical mass generation. Can you comment on its relation with the geometric and topological mass generations?
Geometrical versus the topological case?
No, I mean there is another mechanism of mass generation called symmetrical mass generation.
Symmetrical mass generation.
Without involving any symmetry breaking within an anomaly-free symmetry group.
Anomaly what? Anomaly-free symmetry group?
Abelian-free.
Anomaly-free.
Anomaly-free abelian group.
No, anomaly-free symmetry group.
Anomaly in what context? What is the
For fermions.
For fermion. For fermion, what? For fermion mass generation?
Yeah.
Yeah, probably. I'm not familiar with what you are talking about. So, in the beginning of my slide, I mentioned in one slide we know for the standard model fermion, comment here. The standard model fermion has the left and the right hand components. It's like a Dirac fermion has both left and the right hand component, and each left and right hand component is a wild fermion, and you can form up. I mean, QCD, you can form up a quark mass term, right? the gauge invariant quark mass term, the Dirac mass term, which is gauge invariant, which is totally allowed, and it can be arbitrarily large actually. So you can also take the mass sensitivity in QCD. But however, in the whole standard model, we have S22 cross U1, and the left and the right fermion are distinguished by parity, by weak interaction. So that forbids us to formulate a tree-level Bell mass term for quarks or leptons. We need to introduce the Higgs boson and suit the Yukawa coupling, as I mentioned here. That's for the fermion mass generation. So I'm not sure what you are talking about, for what type of fermion mass generation.
For example, is the CPT symmetry can constrain mass generation.
CPT is valid for any quantum with this quantum system. It's not my concern here. So you have to, I don't understand the question. Maybe we can talk afterwards. Because I'm not sure what the fermion you are talking about and what is actually referring to. I mean, here what I'm talking about is standard model quarks and leptons. That's all the only lone fermion we have so far. I didn't comment on neutrino mass. Neutrino mass would be, for example, the Majorana term.
So hi, Professor, and I think this talk is very beautiful. Like formulas is beautiful. My question is, so I'm interested in the formula for standard model.
In what?
Formula for standard model.
Oh, for the standard model.
Yeah, I think it's too complicated, and I wonder if there is any.
The formula for the standard model is too complicated.
Yeah.
The formula for the standard model is given here. I think it's simple.
Oh, you think it's simple?
Probably not simple enough.
Yeah, I think
it's in 4 lines.
I think it's not simple
enough.
I think simple formulas may be 2 lines in 2 lines.
Sorry?
I think when we have
2 lines.
Yes, most less than 2 lines is simple formulas.
Okay.
Yeah.
Sorry? The picture.
So you know, in math class we don't see like 4 lines equation.
Yeah. I mean, I know people complain. Complain the standard model is not simple enough because, for example, the Yukawa coupling here, you have each different Yukawa coupling for every given fermion in the standard model. It's not a single one. I mean, I'm discussing with my friend Bob Holden the other day over dinner. I mean, probably I think the Yukawa coupling is interesting because that allows we have a wide range of the masses for the fermion, starting with the electron and the proton, the U quark and D quark, and the heaviest one is the top quark. That generates the rich flavor physics.
Okay, and I wonder.
Even though, I mean, but however, I want to emphasize. I mean, when I was student, the people emphasize the Yukawa coupling are unnatural because it's too arbitrary. But the Yukawa coupling we have to accept it's, I mean, within the 4-dimensional standard model, renormalizable up to dimension 4, that Yukawa coupling is the fundamental coupling, is the fundamental interaction.
And I'm also
extremely fundamental.
I'm like curious about do you think like the standard model formula can be essentially like cut down to like 2 lines, for example?
I mean, that's some people hope. That's not my concern. My concern is how to break this standard model, bring the new physics.
Okay, and I have another question. And I see in this talk we have many integers, like large integers.
Large integers?
Yes, like 64 or some 73. I don't understand why they are large integers, like in
what integer?
So you can in the formula they are large integers.
You know, which formula?
So in many formula after this.
I mean, those are simple. Right?
Yeah, these are small
less
integers.
Than 5.
No, they are okay, but they are large integers.
Yeah, where you say large integer?
Okay, I think this question is meaningless to answer.
Okay. Thanks.
Is there any other question from other people?
Okay, Paul.
Yeah, I guess we talked about this a little bit, but at very high energies, the cross sections I'm used to go like 1/s at very high energies. And your amplitudes sometimes are not constant; they go like powers of e.
Yeah, yeah.
Um,
Like the graviton amplitude is well known, right? So the mass is graviton in GR, the 4-point goes like e squared.
Yes. You don't view that as a problem?
I don't think that's a problem. I mean, that's the reflection that the GR is along the normal, right? So, but however, I think the interesting, I mean, it was well known that the GR is long-realizable, and the mass is graviton amplitude that has the bad energy behavior. But however, the double correlation tells us there is a connection to the glue amplitude. Glue amplitude has a energy behavior equal to 0. And that has a precise connection. So the renormalizable QCD corresponds to the double copy, reproduce a long-renormalizable GR. So that's something interesting.
But you're saying that's not to be extended to extreme high energies. You're just reproducing the GR result, which is...
Yeah, right now I'm talking about like in this QFT framework, is basically well below Planck mass. If you want to go to Planck scale, then you end up with string theory. So that's medium, like a KLT relation, right? So you still have double copy, that's KLT relation. So I think that actually the double copy is the strong, is the strong prediction of string theory. Because the people complain the string theory has no physical prediction. I mean, if you, through the KLT relation, you take the field theory limit, that gives you, I mean, I'm more interested in field theory. I mean, whatever you have the UV theory. If in a low energy field theory limit, it can give the physical measurable thing. So one side is a glue amplitude, and another side is a graviton amplitude. These two I think we believe is physical. And the glue amplitude has been more than 1,000 times measured at LC. Yeah, so certainly I partly understand your concern. You are more concerned with the much higher scale with the UV complete. What I'm saying is that for any sensible UV theory, you have to give the sensible field theory limit relation. And I think the double copy relation is a prediction of the string theory in a sense through the KLT. That has need to be recognized. Yeah. Even though calculation is harder. On the other side, in field theory, there's in some SUSY type of the gauge theory, supergraph theory, this has been established after the follow order.
Okay. Thank you so much for the questions. Let's thank Professor Hong-Jian again. Okay.